Okay, hello and welcome to my channel. Today we're going to be continuing with the hydrogen atom, and I remember last time that we wrote out the wave function and sort of figured out how our energy would be like. Okay, so today we're going to take a look at the Schrödinger equation for our hydrogen atom. Right, so let's get straight into it. This would be a radial equation, and our V of R, I would take it as minus ZE squared over R, and Z for hydrogen atom is 1. But I will just write, ZE squared over R. Okay, so write out your Schrödinger equation. Square. Okay, now this is it's not h squared 1 minus ze squared over r. These all gonna act on psi. Okay, but the psi now is split into u over r and your ylm. And u here is actually u and l, but we will just use our u of r as u of r. Okay, so use of. Now we're gonna try to do what we did with our quantum harmonic oscillator, which is, well, trying to put the r here into a unit free number. So this, we're going to take r to equal to a naught over 2z. X and x here would be unit free. And a naught is a constant. It is the Bohr radius equal to h squared me squared. These are all constant. And this is unit free. So then we sub it back in. We get to m. Putting what we don't need outside. Wait, no. Z ddx plus, this will be a mess, but I won't be doing it rigorously here. Yes, I think I don't have the energy to do so. Minus z squared. R is a naught to z. Alright, these are acting on our u of r equals to EU. EU of r. Okay, so the final form of it is actually pretty neat. It's d squared dx squared plus l plus 1x squared minus 1 over x. These all acting on u of r equal to minus kappa square of acting on u of r. And here with kappa square is also a negative 1. So this ensures that when you take the boundary condition, and these two would match, and you would actually get a decay instead of a normal wave function. Okay, so it is e minus e. What is it? 2z pen 2z squared e squared over a naught. Alright, so this is your k. If your k is also negative, we can take our boundary condition. So take your x goes to infinity. Here that would means that the second derivative of u would equal to kappa squared u, meaning that u is something like this, kappa x plus minus, so a decay. So that is good. That is what we need. So to further shorten this, we would call kappa x to equal to rho. Okay, and with rho, now we take rho to go to 0 and see our behavior at the origin. Rho now goes to 0. Therefore, that your u have to be something of rho L plus 1 to ensure that it is equal to 0 at the origin. Okay, so see what we have here is e of minus rho, and this is what we need, rho L plus 1. So just as we did for our quantum harmonic oscillator, we're gonna put well, a function here and hope that it would be simple. All right, so your u is now equal to what you have, your function of rho, and what you need. Okay, and of course this guy is going to be put into a series from 0 to infinity, ak rho of k. Okay, so this series, you write it out as, I believe, is a one-step recursion relation. Okay, so it is rho d square d rho square plus, wait, I think I forgot to put this back into rho first. Okay, so we'll do that real quick. So put our rho map here, r to x to rho, so you don't get confused. Just to put this guy back to rho is kind of simple. You have x, you put the kappa outside, so it's minus kappa square d square d rho square. This one is x squared. Also, you put the kappa square outside, rho square. This one has only x, meaning what you get is kappa over rho, all acting on u, equal to minus kappa square u. Okay, and we want to isolate u over here first. So we would divide all of these by k squared. So this term is gone. This is gone. This term is gone. Remember to multiply kappa down in the denominator. That's how you isolate u and get all of those. So I forgot to mention that before we do the rho going to 0 thing. Right, so now back to where we're at. This is 2 k plus rho minus 1, right? K, so it's k plus 1 minus rho. dw d rho. Last part is 1 over kappa, so L plus 1. Is it L plus 1? Yes, it is L plus 1. These all on W equals to 0. Okay, so now we can see the recursion relation here. This is a two-step, and we have a rho outside, meaning this is only a one-step. This could be a one-step, but got eliminated by this rho. So it jumped straight from ak plus 1 to ak. So this is a one-step recursion relation. Okay, it's gonna be ak plus 1 over ak. This is equal to 2k plus L plus 1 minus 1 over kappa divided by k plus 1, k plus 2L plus 2. Right, is it right? Yes, it is. Okay. Yes, it is. Right, so this is your recursion relation. And now we're going to stop here as what we get from this, well, truncation, what do you call that? What you get when you truncate this is a polynomial that we're going to spend time talking about. Okay, so that will be it for today. Goodbye.